Ladies and gentlemen, welcome back to Business Applications for Machine Learning, where we're going to do the practice set for labs D, E, and F. I should just name these different labs. But anyway, practice set number 1, D, E, and F. So we're going to knock out the questions. I think there's about 13, 14 questions in this practice set. And we're going to go ahead and work it out right now. All right, so let's start with the first question. Given the test data and classification model below, construct a confusion matrix. Here's your classification model, visually really easy to see. And here is my test data. All right, I'm going to take my test data, my descriptive columns, run them through this model, and get my predicted values. But first, let me actually get the actual values. The actual values are, so remember, our target column here is animal. Color and height are our predictive columns. So let me just copy that here. Animal, zoom in a little bit, it's kind of small. All right, so we got animal, and that is giraffe. You know what, this would be faster to like this. Now we could work it a little bit faster. All right, so here you go. Let me just write down the actual values. Cheetah. Elephant. First of all, I mean, just from a common sense point of view, this test data is not properly shuffled, so it really doesn't matter for the problem, but I'm just saying, from a practical point of view, it should be shuffled. All right, so this is our animals. All right, and this is our actual, I'm getting this right from the test data. That's our actual values. Now we got to do the predicted values using our little classification model here. Let me zoom in on the classification model. It's easy for you guys to see. All right. I'll actually zoom out a little bit. Just do this. There we go. All right. All right. Okay. I already have the actual values right there. Now, for the first row, color is yellow. True. See? The first row, color is indeed yellow. The height is 12, which is greater than 10. Yes. So this first row is saying, hey, this is a giraffe. If I go by what the predicted values are, the independent values are in color and height, and I run it through the model, this first row is predicted to be giraffe. Again, color yellow, yes. Height is greater than 12, yep. It's a giraffe as well. All right, third row, yellow, yep. Greater than 10, nope, it's 9. Come here, now this is being called a cheetah. All right, we just keep going. Yellow, yes. We're in the fourth row. Greater than 5, no, it's a cheetah. And now we are on the fifth row. Fifth row, yellow, yes. Greater than 10, no, it's a cheetah as well. And again, 1, 2, 3, 4, 5, 6. We're in the sixth row. Yellow, yes. Greater than 10, no, it's a cheetah. All right. Our model is predicting a cheetah. All right. Now we're on the seventh row. 1, 2, 3, 4, 5, 6. Gray, we're following on gray. It's colored no, yellow, nope. We're right on this side. It's gray. Is the height 11? I mean, the height is 11, so is that less than 10? No. That's a false. It's greater than 10. Therefore, it's an elephant. This is predicted to be an elephant. Go here, gray, so it's not yellow, so I go here. Is the height less than 10? Nope. come here. Again, it's characterized as an elephant. Come here again. Is it yellow? No, it's gray. Come here. Is it less than 10? Well, yes, it is less than 10. Come here. It's designated as a monkey. All right, finally, the last 3 rows. Brown, it's brown. It's colored yellow. Nope. Come here. Is the height less than 10? True. Okay, cool. Monkey. All right, brown. Boom, not yellow. Come here. Less than 10. Yep. Monkey. And finally, brown. Nope. Less than 10. Yep. Monkey. All right, cool. So now we have, remember, this is saying, given the test data and classification model, construct a confusion matrix. So now what I've done is, I've gone ahead and I've gotten my, just a little bit, I had my actual values, and now I've got my predicted values. From here, I'm now going to create my confusion matrix with the actual values and predicted values. This is basically how the table command, you know how we use a table command to create a confusion matrix? That's what we're basically creating. So let's go ahead and do it. Across down the rows, we have our actual values. Let's do it in alphabetical order. So just like the table command does it, so it's going to be cheetah. And our part does like that too. Elephant. I hate how it does autocorrect. Pisses me off. Elephant, cheetah, giraffe, and the monkey. All right. Move that over. And of course, now our predicted columns. Monkey. All right. By the way, I should probably say this is number 1. Number 1. All right. Okay. All right. That's how the confusion matrix is going to be labeled. Remember, across the rows are actual values, down the columns are predicted values. All right, so let's do this. In our data, how many actual values of cheetah were there? Right, this column is the actual one. There are 3 values. There are 3 actual cheetahs. Right, there are 3 actual cheetahs. Here they are. Here's the actual cheetahs. Let me just fill in the color to get a little fancy. All right, there. So here are our actual cheetahs. All right. Now, what was the actual prediction of the actual cheetahs? Okay. So for the actual cheetahs, I got 3 of those actual cheetahs were predicted to be cheetahs. Fantastic. So I'm going to put 3 here. See that? For those actual cheetahs, all 3 were predicted correctly. Excellent. All right. Let's move on to the next one. Elephant. Elephant. These 3 are the elephant ones. All right. So for the actual elephants, how many were predicted to be actually elephants? 2 of them. Elephant, elephant. First 2 rows. So I'm going to put 2 here were predicted correctly. And 1 of those actual elephants was incorrectly predicted to be monkey. Let me get rid of this now. Monkey. So here I come here, and I put a 1 there. See that? Next row is giraffe. I go to giraffes, the first 3. How many giraffes were predicted correctly? 2. So come here to giraffe, 2. All right. And 1 giraffe was predicted to be a cheetah, so I put 1 there. Right? You see how this is going? The actual value is controls the row, so I go down the row and I just simply put the number that was predicted correctly, and the number that wasn't predicted correctly, I put it in its respective column. So because this is giraffe, this is supposed to be a giraffe. I'm here, but it was predicted as cheetah, so I put the 1 there. And finally, monkey. I come to monkey. All 3 monkeys were predicted correctly. Bam. All right. And because we have a total of, 12 rows, we should make sure we have a total of 12 values here. And we do. All right. And we know we got everything. Now, This is our confusion matrix, so you're done with number 1. But we got to use this confusion matrix now for my rest of my questions. Not rest of my questions, but number 2, 3, and 4, and 5 are excellent. So number 2 is now saying, okay, given the confusion matrix number 1, what is the accuracy of the classification model? You guys know this. The accuracy is simply the sum of the diagonals, because remember, everything on the diagonal is predicted correctly, divided by the total number of confusion matrix. So across the diagonal, I got 3 plus 2 is 5, 5 plus 2 is 7, 7 plus 3 is 10. I got 10 divided by 12, right? Which is going to give me a value of, and in the exam, guys, I mean, just put the fraction 10 divided by 12. You don't have to put the whole answer. I will go ahead and do it just for kicks, right? But I'm fine with you just putting the answer, you know, whatever 10, 12 is, but just so you guys can see it. So it comes out to, the accuracy came out to 0.833, right? Whatever that is. What is the error rate of the classification model? Again, you guys know this as well. The error rate is simply 1 minus the classification rate. I'm sorry, the accuracy. And so 1 minus 10 over 12 literally just gives you 2 divided by 12, right? If you know your simple fractions. And again, you can just leave your answer like that. You don't have to do any math. As long as you know the fraction, I know you understand. If you know how to do, if you put 2 over 12, I know you understand, right? Number 4. Given the confusion matrix, what is the precision rate classifying the elephants? My BAP students, you guys should be like on top of this. So what is the precision? All right, precision has to do with, so what is the precision rate classifying elephants? I could have chosen anyone, I just chose elephants. What does the precision rate have to do with, guys? The precision rate has to do with if something was predicted to be something, it was actually that something. And if you look at the confusion matrix, it goes down the column. So basically, for elephants, it's 2. It's whatever was predicted correctly, which is 2, divided by the whole column. Well, the whole column, in this example, there's no other value, so it's literally going to be 2 divided by 2, which is 100%. Right? 100%. And it's cool to see this because this goes to the heart of showing you the difference between precision and recall. Right? Precision and recall. There are 3 elephants, but only 2 were predicted to be elephants. But what precision is always talking about, or the precision of elephants, a particular class in this case, right? It's always talking about, hey, if the model says something is an elephant, then damn it, it's an elephant. It might not find all the elephants. That's recall. That's recall. It might not find all the elephants, but if the model says, hey, I predict this to be an elephant, damn it, it's an elephant. In this case, it was 100%. 100%. Remember, like I always say, my BPA students, you know this. My BAP students know this. Precision and recall are polar opposites of each other. In terms of machine learning, we obviously want both of them to be as high as possible, but they tend to be opposing forces, right? So in a business case, you always want to choose one over the other, right? You always want to have one be 100% over the other. You have to always talk down the board or management, the executive board, about, hey, look, yes, both are important, but this one's live or die. One, either recall or precision is live or die, right? In terms of what your business strategy is. All right, and that leads to our next question for number 5. What is the recall rate classifying giraffe? All right, again, recall rate has to do with finding all the instances of giraffe. How good was it at finding all the instances of giraffe? So in this case, how many instances of giraffe they actually were? 3, right? So now we do the math. So the numerator, again, is going to be the same. Basically, what was actually predicted correctly, which is 2. And this is now going to be divided by the whole row. That's recall is row. Recall precision is column. So this is going to be 2 divided by 3. And that's my recall. So my recall is going to be roughly 67% for giraffe. 67%. So basically 67% of actual giraffes in my data elements were actually predicted to be correct. Were actually identified correctly to be giraffe. All right, and so we just knocked this out. Fantastic. All right, number 6. When creating the training data and testing data from a data set, which one is larger? You guys remember that? Right? In our lab, we had to take our data set and we shuffled it and then we divided it. And in this case, I divided by 70%, 30%. Our training data is always larger. Our training data is always larger. All right? Our training data is always larger. Larger. Our testing data is always smaller. All right, if the min bucket is set to 20, which one of the nodes below will our part not split? All right, number 7 is a good one. If min bucket is set to 20, which one of the nodes below will our part not split? Now, remember, min bucket is basically the size of the table before you split it into 2 different subtables or into 2 different nodes, subnodes, children. Min, oh, this is a typo. This actually should be min split. This shouldn't be min bucket. This should be, let's see. Oh, I have a typo in both of these. I'm gonna have to post this. All right, guys, I have a typo in both of these. So I'll correct it and send it out again. But here, this should be min split. Here in 8, this should be min bucket. All right, I confused myself. All right. So guys, first, let me write the question down correctly if you're following along. So this should be the correct. I don't like that. Let's merge cells here. Okay, good. Excellent. I don't know why that 1 is there, but okay. If the min split, not min bucket, guys, min split is set to 20, which one node below will our part not split? All right. So here, if the min split, now that we corrected the question, what that means is that the main table before splits into children. It's a left node, right node into the children, into the different sets, like we did when we were working out the algorithm in our part in the lab. The main table before we split it, and in our root node, it was data train, but it doesn't matter if it's a root table or any other node. Anything that's going to be split, the min bucket decides, hey, is the first check to see, hey, should this be split? Is there enough data points? So the default is set to 20. So in this case, node 1, it has 10 cherry items, 5 mango items, and 6 orange items. Summation of 21. So node 1 is fine to split. It meets the criteria. All right. So I go to node 2. Node 2 has 9 plus 5 plus 6 items. That's 11 plus 9. That's 20. That is also fine. Remember, 20 is that whatever that value for min bucket is, that's the minimum. That's fine. As long as it's 20, we're good. Node 3, finally, we get to 19. That violates it. It's too little. It's too small. So node 1, yes, split. Node 2, yes, split. Node 3, no split. All right, that's how we do it. And again, I'll send an announcement and I'll recorrect in the PDF how it's written and send it out. All right, so number 8, this goes to now number 8, where we have the other mistake. And so in 8, the question is, given the R part, scroll a little bit, given the R parts that given that R part is searching a numeric column for a splitting value, and that the min split, this should be actually min bucket, is set to 8, which unique values will R part test for Gini impurity score for? All right. So again, I'm going to copy this, and I'm going to write the correct question right here. I don't know. Okay. I don't know why it does that. All right. And now we're going to change this to min bucket. The min bucket. All right. And let me copy some of these values here so you can see it. So can I do it? Oh, let's just do it here. All right, we'll just do the math here. So which unique values will our part test for Gini impurity score? Now look, here's the unique values on the top row. Down here's the number of occurrences of each one. Okay, so I have to go through each unique value and see if it meets the cut of the min bucket value, which is set to 8. I come to 2. The first value is 2 in the unique values. All right. The rule will be, if I test that, the rule will be less than 2, greater than or equal to 2. Well, greater than or equal to 2 are all these numbers. It will be all these values. So we're good. But less than 2 is what? There is no value less than 2. It will be 0. No. Violates the rule. Move on to number 3. 3. My 2 splits will be less than 3, greater than or equal to 3. Okay, greater than or equal to 3 are all these values. 1 plus 4 plus 6 plus 5. Whatever that table will be, it'll have all these rows. It's good. But the less than 3 one will only have 3 rows of data, 3 occurrences of the values here. They'll all be 2s, right? But there's only 3 of them. It violates it. Move on. Number 5. I'm testing I'm testing the rule less than 5, greater than or equal to 5. Again, less than 5 gives me one row of 3, 3 rows of 2 for only 4 rows. Doesn't make the cut. Finally, I get to 7. The rule for 7 will be less than 7 on my left side and greater than or equal to 7 on my right side. So less than 7, right, is going to give me the values 4 instances of 5, 1 instance of 3, 3 instances of 2, for a value of 8. And finally, 7 makes the cut. Right, so we actually will start, our part will start by testing the splitting value, calculating the score, the Gini scores for the 2 children created by splitting 7, less than 7, greater than or equal to 7. And greater than or equal to 7 also makes the cut because there's 6 values in 7, and then 5 here, 11 we're already good. Now let's go to 8. Okay, so 8, if 7 makes the cut from less than 7, less than 8 will always make the cut, will also make the cut, so I'm good there. I have to test the greater than, which is going to be, remember, it's greater than or equal to 8, so that's 5 occurrences of 8, 3 occurrences of 9, which gives me exactly 8, so 7 and 8 is good too. And finally 9, less than 9 is good, because 7 and 8 are, but greater than or equal to 9 will not be good because I'll only have 3 occurrences of 9, which is not enough, which will not be enough rows. Therefore, the only 2 values that our part's going to test for split by is 7 and 8. And that's why the answer will be just 7 and 8. Those are the only ones that make the cut. All right, number 9. Number 9, given the classification model below, what is the root error, node error, or baseline error? All right, remember, I literally just took the same graph. It's basically, we start with our root node. In the case of our lab, it was basically our data train model, or whatever our initial table is that we're training the model with. And we break out the target column, or the column we're trying to predict, and we just count up all the unique values. In our case, is the flowers, right? We had 27 setosas, 38. And remember, the way these numbers come out, right? It's literally going to be alphabetical order. The first number is setosa. The middle number will be versicolor. The last number will be virginica. If there's 8 values, I don't care. It's all going to be still alphabetical, right? The key will tell you. Or the bottom boxes will tell you. All right, so in this case, I have 27 setosas, 38 versicolors, 40 virginicas. The virginicas are the most. Therefore, this box will be considered to predict virginicas. And what that means is basically, look, if we just had a one-cell prediction model, right? What would the rule be and what would the prediction be? By default, it would end up being virginica because there's only 40. Okay? So it's a Virginica node. If it's a Virginica node, therefore Setosa and versicolor by default are mislabeled. They're wrong. So how many total flowers are mislabeled in my root node? 27 plus 38 gives me 65, right? So 65 out of the total, what's the total amount of flowers or rows of data we have in our root? 105. So 65 out of 105 are mislabeled. Whoa, whoa, what's going on there? And put it, I think it's treating it as a date or something. Or is it reducing it? I don't know. Stop. And put it in quotes. All right, and in the exam again, you can just leave it as this fraction, and we're good, right? The actual number, as you guys know from the lab, it comes out to something like this. And guys, this is our root node and baseline error, and we carry this now throughout our part splitting when we calculate the relative error, right? Which is basically going to be the error rate at any point divided by the error rate of the training aspect divided by the root node. That gives our relative error. Hence the term relative. Relative to what? Relative to the root node error or the baseline error. So this is it right here. All right. So that's number 9. Now number 10, using the classification mode in number, well, I said mode. This should be model. Using the classification model in number 9, calculate the relative error after the first split. All right, calculate the relative error after the first split. So the first split we have, it's here and it's here. And we did this before and we'll do it again. All right, we did this in the lab and we did it before. We did it by hand and we'll do it again. We'll rock it again. So number 10. All right, when I have to do the split, after the first split, I have to calculate the relative error. What I first need to do is calculate, create my confusion matrix. After I can create my confusion matrix, then I need to calculate the error rate. Once I get the error rate, then I divide simply by my root or baseline error, and I'll get the relative error. All right, so here, start with our confusion matrix. So again, follow the alphabetical tone they said. Setosa, versicolor, Virginica. Setosa, versicolor, Virginica. Virginia. Nice. Virginica. All right. Now this is going to be slightly different than when we create a confusion matrix. When we do our predictions, when we compare our predictions to our actual values, right? This is going to be slightly different because this is happening on the trading model. The way this works is the split at each node. So look, here's the root child. We had one split. So essentially you just have this and this. These two don't exist yet. All that exists is this, this, and this. The root node, the first split versus color here, 27330, and the Virginica. Right, so those are the only 3 nodes that exist. So what we do is we always take the child nodes. We always take the leaf node. The leaf node. So in this case, after the first split, this is our leaf node, and that's our leaf node, and that's it. And then we take the leaf nodes, and we simply use them to create the confusion matrix. And in this graph, it's actually very easy. You take here's the versicolor. This is the versicolor node, right? Why is the versicolor node? Because 33 is the largest number. 33 represents 33 versicolors. Bam, easy. So because this is the versicolor node, I literally go to the versicolor row right here. And I put those values in. 27 Setosas. All right. 33 versicolors. And 0 Virginicas. It is that simple. That simple. I go to the other child node, which is Virginica. Why is it Virginica? Because 40 is the largest number, and that number is representing the Virginicas. Okay? So here, again, I'm going to go to the Virginica row, put in 0 for Setosa, 5 for versicolor, and 40 for Virginica. That's it. I have no, after the first split, I have no other children nodes. I have no other children nodes, right? That's it. Because I have no other child nodes and no child node was Setosa, this all becomes 0. And now I'll have my confusion matrix. Now you guys know this. I keep repeating this. From here, how do we get our error rate? First, right, get your, I mean, again, I keep saying get the accuracy and do 1 minus accuracy. That's one way to do it. Or you can simply, another way to do it is just add up all the numbers that are not on the diagonal. Right, another way to do it is add up all the numbers that are not on the diagonal. So these values, actually, let me get a little fancy. Show you guys another way to do it. So it could be literally this value, this value, this value, and this value. All right, everything that's gray, right, that's not on the diagonal. That's not on the diagonal. So basically what I could do is, I mean, I could do it the way I showed you guys before, get the accuracy, subtract 1 from 1 minus accuracy and get your error rate, or you could simply just add all the values that are not on the diagonal and divide that by the total number. So in this case, the 0, 0, 0, 5 plus 27 is going to be 32. And so my error rate is going to be 32 divided by 105, right? Which is just going to be the same as that number right there. All right, that number right there. Oh, wait, hold on, sorry. Yep, the sum of everything is 105. Right, and you can see that we got the same way, because if I do it the normal way, accuracy will be 73 divided by 105, and obviously that's just going to be right, and if I simply do 1 minus that, I get the same value up there. So I'm just showing you guys how you can write the fraction in the exam. It's just easier. It might be a little easier that way, or you guys can work out the math. You can get the fraction 73 over 105, and you can do 1 minus that, right? And just get the same answer. All right, either way you guys want to do it. It's fine with me. All right, so I have my error rate. I have my error rate now, right? Now, am I done? I now have to do what to my error rate? I have to divide it by my baseline error. Okay? So, all right, so we have our error rate, and now the next process is very simple. From our error rate, to get my relative error, it's going to be simply my error rate divided by my root node error or my baseline error. We have that already. So it's basically going to be my error rate at this point divided by my base error or my root node error. Bam. That is my relative error for the first split. For the first split. We're going to need that now for our other problems. But first, in number 11 now, calculate the relative error after the second split. All right, no problem. So just like before, I'm going to look at my split. So after here's the first split, here's the second split. Now after the second split, how many leaf nodes, how many leaf nodes do I have, guys? The end nodes. 1, 2, 3. Fantastic. Setosa, this one, 27, this is a Setosa one because 27 is representing Setosa. It's the largest one, it's Setosa. Versicolors, 33 is the largest amount of versicolors. Virginicas, 40 is the largest amount of Virginicas. Boom, let's get to work. So just like before, just copy and paste this. All right, delete this. And let me get rid of these formats. All right, so let's start with Satosa. 27 Satosas, everything else was 0. Zero, 0. All right, now let me go to my versicolors. All right, excellent. In the versicolor row, I had 0 Satosas, 33 versicolors, and 0 Virginicas. Excellent. And finally, Virginica. My Virginica row, I have 0 Satosas, 5 versicolors, and 40 Virginicas. All right, and now we have values in each row because now we have 3 notes. And here you go. Bam. My second split. My second split. What is the accuracy, guys? I'll do it the old school way. Accuracy is 27 plus 33 plus 40, which gives me 6,100. So my accuracy is actually 100 divided by 105. Oh, there he goes again doing that. Annoying me. All right. If I just do the math, it comes out to 95%. Not bad. Not bad at all. Okay. What is my error rate? Simply 1 minus that, which is going to be 5 divided by 105. Or mathematically it comes out to 5 divided by 105. All right. Excellent. All right. And so what is my relative error now? Right? It's going to be this value divided by my root node error. Again, always with the root node error. Where is my root node error? Right there. All right, let me make sure I divide it by, excellent. Okay. So it's this divided by that. Hold on, let's make sure I did the math correctly. All right. Okay. All right, guys, I don't know what's going on with the calculation here, but this is not the right number. Like if I were to type this number into R, let me copy this. This divided by that should not give me 0.667. I don't know what I'm doing. Let's try this again. This number divided by that number. Okay, yeah, that's the right number. So that's the right number. I don't know what I wrote in here. Yes, I don't know what's going on there. So that's the right answer right there, guys. Yeah, I apologize for that. So that is the right answer right there. Again, I don't know what's going on with that cell. So that's our relative error after our second split. So this is our relative error after the first split right here. This is our relative error after cell C45 is our relative error after first split. Cell D53 is our relative error after the second split. Now, we're ready for our questions 12 and 13. For number 12, using the model, what is the cost of complexity after the first split? Yes. All right, yes. Let's clean this a little bit. So after the first split, so when there's 0 splits, our relative error, let me just write splits relative error. All right, just so it's easier to see, and CP, the additional cost. Now, for our initial split, 0, our relative error is 1 for a root node. Okay, there's 0 splits, just one root node. The relative error is 1. That's easy to see, right? Because this is the error of the root node, and that divided by itself, it's 1. Okay, easy. Now, the question is, after the first split, what is the cost of complexity? All right, what's the additional cost of the complexity? That answer goes here in our cost of complexity table, in our part, in our part. When we do the print CP, you will see that answer over here, because remember, the cost of complexity and the complexity parameter to check it, they are post-pruning parameters, all right? Post-pruning parameters. So to get that answer, right, we need to get our relative error. So after the first split, our relative error is what? It is this. So let me just literally do equals this value right there. All right. So how do I get that? It's going to be this minus that divided by, so basically the reduction in the relative error divided by the increase in splits. In this case, there's just been one increase in split, which gave us this reduction in relative error. So what was the cost of that complexity? Well, it's basically going to be 1 minus this number divided by the increase in the splits that reduced it. So our increase in split was literally just from 0 to 1, so it's literally this number divided by 1. And so that's pretty much easy. So my cost of complexity after the first split is that number right there. I could have just done the math right there, but whatever. Right? I wanted to show you guys this 2 steps. It's a 2-step process. What's the reduction in relative error from our previous relative error? And then dividing that value by the increase in splits. In this case, it was just by 1. You'll have situations where your splits can go from like 5 to 7, 7 to 10. And so that's why you need to include that second step of dividing by the net increase of splits. All right, and that is basically my number 12, my cost of complexity after my first split, and now number 13 after my second split. What is my cost of complexity? Same calculations again, guys. Right here now, I will simply let me just take this, copy it, bring it down here. Oh, like that. All right, whatever. I'll just delete this. Move that up there. There you go. All right, so 13 will be this answer right here, whatever that answer is right there. And what's the answer going to be? Well, what was my new relative error right here? How many splits are there? First of all, we went from 1 split to now it's 2 splits. We went from 1 split. First we had 0 splits, then we had 1 split, and then we went from 1 split to 2 splits. All right. And our new relative error was this value right there. All right, so what's that going to be? It's literally going to be this minus that divided by my increase in splits, which is 1, to give me an answer of 41.1438, whatever, etc., etc. So after 2 splits, that was my cost of complexity, right? And if we keep working this, as we saw in the lab, we'll eventually get to a CP level that's going to be whatever we designated. Like in this, the default case would be 0.01. If we set it to 0, it would end up being 0, etc., etc. All right. So that's the cost complexity after the first 2 splits. Finally, number 14, to make a larger, deeper tree, should you make complexity larger or smaller? Right, to make a larger, deeper tree, you just want to make them, it should be, should you make the complexity parameter larger or smaller? So to make a larger or deeper tree, should you make the complexity parameter larger or smaller? The answer is obviously you make it as small as possible, smaller. To make a larger, deeper, or deeper tree, your cost of complexity to make a larger tree, cost of complexity should be smaller. All right? And you guys saw that also with the labs. And finally, number 15, I have this data table. I've given a data table, data.table, named fruit.train. Given a data table named fruit.train. All right. That has the column sugar.levels in it. I don't know what other columns it has, but it has sugar.levels in it. Which is a numeric column, in it. Okay, so sugar.levels is a numeric column. The breakdown of the unique values in fruit.train is given below. Write the code to find the splitting value that would give the smallest Gini impurity score. Assume our part is using the default values for min bucket, min split, max step, and CP. Okay, excellent. There's an additional, so I gave you the column name here. There's an additional column name you need, which is basically the target column. In this case, it'll be fruit. So I just assume that column name is fruit. And it's basically the code we wrote before. And I'll write it for you again. So here, I'm just create a new script file here. And like I said before, the name of the table is fruit.train. Right? That's the name of the fruit.train, and it has the column names sugar.levels. And here I didn't tell you what the target, I should always tell you what the target column name is. Here I didn't tell it to you, but let's assume it's just fruit. All right, so that's what we're trying to predict. We're trying to predict fruit by sugar.level. That's one of the columns. That's the one we're focusing on in this case. All right, now write the code to find the splitting value that would give the smallest. So we're not, assume, we could obviously use our part to do this, but I want you guys to write the code or give the lines of code that gives you the value that we're looking for. That finds the splitting value that gives the smallest Gini's impurity score. All right, so here's my unique values. So right off the bat, so these are my unique values, obviously in sugar.levels. All right, so right off the bat, if I'm using the default values, the default value for min split is 20. So let's do the math. 3 plus 1 is 4, 4 plus 4 is 8, 8 plus 2 is 14, 19, 20, 22. All right, so the table fruit.train looks like it has 4, 8, 14, 19, 22 rows, and it makes the cut. Remember, the minimum is 20. All right, now we do the min bucket. Min bucket, all right. This less than 2, 0, less than 3 would give me 3 values. Nope. Less than 5 is 4. Nope. Less than 7 is 4 plus 1 plus 3, which gives me 8. Yes, 7 is good. I go to 8 is going to be good. Greater than 8 is going to be 8. That's fine. 9 with 3. All right, excellent. So there's only 2 values I have to test, basically, guys. 7 and 8. 7 and 8 are the only. This becomes between 2 values, 7 and 8. All right. And I didn't give you the table. I didn't give you the table, but if I had given the table, we could actually have worked the code through it, but that's fine. All right, from here, I know what I got to do. So f dot array would basically be what? It would be fruit train, the sugar levels, I don't have to make it this fancy, but I just want to make it, I don't know, depending on the question you guys get on the exam, I want to make it as proper as possible. And remember, we want the unique sugar dot levels, and also in the code, I sorted it right in here as well. All right, so we get 7 first and then 8. Again, don't need to do overkill. It's only 2 values. Don't need to do overkill. But again, I just want you guys being ready for the exam. All right, so I have my f dot array. Now I'm going to create a vector, an empty vector to store the values. And now I'm going to loop through my table. And the name of the table, again, is fruit.train. Not loop through the table. I'm going to loop through my f dot array, which is going to literally just going to be, in this case, going to be just 7 and 8. All right. And now I have to do, let's start with my left node. It's going to be fruit.train, all the values that are where sugar level is less than 7. 7 is our first value, so less than I. Right? I want basically the count, right, of all the values, and I want it by equals fruit. That's why I said we need to know the target column, fellas, by fruit. I could do the same thing for right node right here. But for right node, it's going to be sugar levels greater than or equal to I. All right, done. Okay. So I have, all right, I just said it did it for just the first split, all right? So I have my left node, I have my right node. Now I have to do the math to get the Gini score. If you guys remember, the formula is literally going to be n dot sum of n. That's going to be my p, and then I'm going to take this, square it. So this is p dot square. All right, so this will end up being p dot square. Each individual n value divided by the summation of it. Square that sucker. All right. And then to get the Gini score for the left node, it'll be simply going to be all the rows, 1 minus the sum, p dot square. All right, I got my left Gini. And for my right Gini, it's going to be the same one. Same concept. Nothing special there. And that's the beauty of code. All right. So I got my right node, I got my right Gini, I got my left Gini. Right, now all that's left is for me to get the weighted average. To get the weighted average, I need my total I need the n. I need the total amount of n's, which is going to be basically fruit.train for all the rows. Just give me the count. Alrighty, and my left dot n is going to be for the table left dot node sum up n, how many values there were there, and my right dot n is going to be my right node, and I want to sum up the n values there as well. All right, and now I'm ready. Now I can take my weighted average GS score, or at least this first one will be 7. And this is just literally going to be GS equals, let's do the left one first, left dot n divided by total dot n times whatever the left side Gini score was, plus right dot n divided by total dot n times right dot Gini. And now I have it for 7. This is the GS score for 7. I want to save it because the next loop is going to do it for 8. And this is going to be basically Gini scores, append the bad boy, GS, and bam. Gini scores now has my, it's going to have my Gini scores for each one. And to get the smallest one, I'll just create the table, let's call it FDT. Will be, the values will be f dot array. And my Gini scores will be Gini.scores. And to get the smallest value, again, I'm going to use the which.min function, and that's literally just going to be which.min on the Gini column. And that's going to give me the row with the value and the smallest score. So again, there's only going to be 2 rows in there anyway, 7 and 8, right? But still, again, keep it dynamic so that you can handle anything. So that's basically the code. And this is our number 15. It's very similar to our other lab. Hopefully you guys understood it, and you guys understand how to work with the code to make the changes you need to calculate any other kind of Gini score, split, or splitting value this goes on. All right? All right, excellent, guys. So from here, we're done with our practice set D, E, and F. And hopefully you guys should be ready for the midterm. All right, I'll see you guys later. All right, bye-bye, guys.